It's actually crazy, but 9 out of 10 students get questions about networking concepts wrong in the exact same way. And it quietly, almost invisibly, costs them their top grade. What happens is they write down this vague, generic answer that sounds kind of right in their head, but the examiner's mark scheme? Yeah, it absolutely demands precision. Welcome to this explainer. Today, we're diving deep into how to fix those exact blind spots. We're going to lock down exactly how to answer questions on network interface cards, MAC addresses, and network protocols, so you literally stop leaking marks. Let's look at the mistake right before it happens. Okay, let's look at a classic comparison. Imagine you write, a MAC address is a network number. Well, the mark scheme gives that a big fat 0 because it is just way too vague. But what if we tighten that up? A MAC address is a unique identifier assigned to a network interface card, or NIC, for communication on the local network. Boom, that secures full marks. Why? Because it's precise, it uses the right terminology, and it anchors the whole concept to the actual hardware, the NIC. All right, Section 1, the full marks framework. So moving from a 0-mark answer to a full mark answer definitely doesn't happen by accident. It takes understanding the specific frameworks and cycles that examiners are actively hunting for when grading your responses. Think of the 4-prompt structure and the 3-pass revision cycle as your ultimate diagnostic tools. When an examiner reads your paper, they want to see you explain what a concept is, exactly how it works, where it's used, and why it's the best choice for that situation. Following this visual pathway completely prevents those weak, generic exam habits because you are automatically anchoring every single explanation to a real-world scenario. Let's break down this 3-pass cycle real quick. Step 1, you absolutely must secure those precise definitions. No wiggle room. Step 2, rehearse the diagrams and worked examples until the mechanics are basically second nature. But step 3, that is where the magic happens. Practice scenario adaptability. Look, if an exam question specifically asks about a school network, your answer has to talk about how students or teachers use that specific network. If it's a database server, relate it back to data retrieval. Anchor your technical explanation to the context they give you, always. Moving right along to Section 2, decoding data representation. Let's apply this rigorous framework to the exact places where binary and hexadecimal marks just seem to vanish into thin air. Hexadecimal is a perfect example of this real-world application. To get full marks, you can't just write hex is shorter and call it a day. You have to build up from a precise definition, explain the underlying mechanism, provide a scenario, like say an error code or a MAC address, and finally state an examiner's safe advantage. So, because hexadecimal is more concise than binary, it drastically reduces the likelihood of human error when programmers are typing in or reading memory addresses. That is a full mark answer. Now let's talk signed integers, specifically 2's complement. There is a massive red pen trap here that catches so many people out. Students often treat the most significant bit, the one on the far left, as just a simple plus or minus sign. Actually, scratch that. It is absolutely not just a sign. It has to be treated mathematically as a negative weight. So in an 8-bit number, that bit carries a mathematical value of minus 128. So the trick to never losing precision here is to follow this exact mechanism safely and accurately. Step 1, check that most significant bit. Step 2, if it's a 1, immediately assign it a value of minus 128. Step 3, just add the remaining positive bit values together like you normally would. For example, if you have a 1 followed by all zeros, the answer is just minus 128. It's this step-by-step mathematical approach that the mark scheme rewards because it takes all the guesswork out of it. All right, Section 3, networking and transmission traps. This is another major area where marks are frequently dropped, especially when we get into transmission modes, NICs, and media access control protocols. When you're hit with a question about simplex, half-duplex, or full-duplex transmission, please don't just write data goes both ways. You have to identify the exact task, logically sequence how the data flows, and strictly anchor it to a specific device from the scenario. Think about a walkie-talkie. That's half-duplex. Why? Because data flows in both directions, but crucially, not at the exact same time. And that brings us to the protocols actually managing all this traffic. MAC protocols regulate access to shared communication channels. Basically, devices that have network interface cards, or NICs, use these MAC protocols to actively listen to the medium before they transmit a single byte of data. If the channel is idle, awesome, they send. If it's busy, they wait. This is called carrier sense multiple access, and it's entirely designed to stop data collisions and keep network performance running smooth. This listening process is especially vital in wireless LANs, operating under those IEEE 802.11 standards.
For computers to talk wirelessly over radio waves, you need a few key components working together: a wireless router or access point, your wireless clients, the NICs installed inside those clients, and a very specific protocol called CSMA/CA. That stands for Carrier Sense Multiple Access with Collision Avoidance. If you understand how those pieces physically and wirelessly link up, you literally understand the backbone of the entire network.
Section 4, Protocols and Communication. So, how do all these devices actually talk to each other without it turning into total chaos? Well, they use specific, highly structured protocols. I highly recommend using an application-first methodology when studying this stuff. When you're explaining a protocol suite like TCP/IP, always start with the real-world digital problem it's trying to solve. Don't just dump a list of acronyms on the page. Identify the requirement first, like sending a really large file across the world. Then explain how TCP breaks that file into reliable packets and how IP routes those packets to their final destination. Connecting that technical sequence back to reality, that is exactly what unlocks the highest marks. Think of your understanding in 3 distinct layers. At the bottom, you have your everyday explanation, just describing the concept simply, like you would to a friend. But to hit that A-star level, you have to climb up to the technical explanation. You got to use precise vocabulary like bandwidth, latency, and routing protocols. Finally, at the very top is the exam explanation. This is where you shape that technical idea into a structured, scenario-based response that directly checks off boxes on the examiner's mark scheme. Finally, Section 5, the exam strategy edge. To wrap up this explainer, we need to quickly decode the specific command words the examiners use. Because, let's face it, knowing the tech is only half the battle. Knowing how they test it is the rest of the game. A classic trap that will severely cap your score is treating an explain question like a define question. Look, if the prompt says state or define, they just want a concise meaning. One sentence, boom, you're done. But if it says explain or describe, you have to set out the purposes and back them up with actual technical evidence and reasons. If you just drop a short label when they ask you to explain, you are leaving so many points on the table.
Here is one last massive red pen trap: confusing similar terms. Validation and verification are totally different things. Validation is a computerized check to make sure data is reasonable and meets certain criteria, like checking if a date of birth actually happened in the past. Verification, on the other hand, checks that data hasn't been corrupted during copying or data entry, like when you have to type your new password twice just to make sure it matches. Swap those 2 terms on an exam, and it's a guaranteed way to lose points. Keep them distinctly separated in your mind.
So, what does this all mean? Well, if this explainer made these concepts click for you, make sure to subscribe to Ace the Exams at acetheexams_IGCSE to absolutely crush your Cambridge examinations. Let's end with a quick interactive challenge for you. A school network is experiencing serious data collisions when multiple computers transmit simultaneously. Using the frameworks we literally just covered, how would you explain the role of CSMA/CA in solving this? Think about it and keep practicing.